Hello everyone, welcome to Snippet Nugget, and in this video we are going to discuss about binary search. Okay, binary search, and also we will see about how the time complexity for this is derived, and we will compare it with the ternary search. Also, we will analyze why it is a common prevalence or a common practice to factor everything by 2. For example, in dynamic array, we double the size of the array at each full array case. In a similar way, in a binary search, we split the array into 2 parts. Why don't we, triple the size of the array, or why don't we split the array into 3 parts during the searching? Okay, so why only 2 is selected? Why binary search? Why no ternary search we generally hear or we generally practice and see? So we will discuss about that aspect also. So please be with me till the end of this video. We will look at the binary search first, and we will compare it with the ternary search. We will derive the recursion formula for both of them, and then we will compare the mathematical output for both the searches, like the time complexity of both the searches. Okay, so let us start then without wasting any more time. What is the input in this situation? In this situation, we have a sorted array, okay, ARR, and we have a number X, which we need to search. If that number X is found in this array, then we return the index of that number. Okay, if it is not found, we will return -1. Simple, right? We know now input and the output. Okay, so let me just give you one example. If my array is, let us say, 0, 2, 3, 9, and 11, and if I want to, so this is my ARR array. If let us say my X is 1, okay, so obviously 1 is not in this array, so my output will be -1. If I'm searching for, let us say, 11, so 11 is present at the index number 4, so my output would be 4. Okay, so this is our case. We apply generally binary search in a situation when our array is in sorted order. So what is a binary search in a sort form? We basically, let us say, if our array is in sorted order. Okay, let me take a very good example of binary search is our phone directory, or let us say a dictionary, we can say. Okay, so let us say we have a dictionary, and this dictionary looks something like this. Please note, I'm explaining it in a term so that it is very much understandable to the small, like a small experienced or a very beginner level candidate. Let us say this is our dictionary. It starts with A, ends with Z. Okay, each of the words are basically arranged in order of its first character. Okay, let us say if you have a word X as a word as, let us say, money. Okay, so now you have to look for money. So what you do as a binary search implementation, you just go to the middle point of the page. Let us say if the dictionary has 1000 page, so 1 to 1000 page. Okay, 0th page and 1000 page. You go to the page number 500, and you see that, okay, what is the word here? Okay, let us say if it says it is F. Okay, so we know that, okay, M, the money, M, the word, it is after F, so you have to discard this side, and you are now interested in the second half of the dictionary. So what you do now, you again find the midpoint in this part, so this is here. Okay, so now let us say again this midpoint you find as page number 750, and you go and see that, okay, what is the letter here, the first letter here? Let us say it is L. So you know that, okay, this is L, so LMN. So L is just before the M, so basically L is before M. So now you know that again you have to discard this part because LM, so M will be occurring after L. Okay, so you are now interested in this second part, which is basically between 750 to 1000. Again you will find the midpoint between them, So what would be the midpoint? 875. Yeah, 875. Again, you go and you see that, okay, let us say this is W. So you know that, okay, M is less than W. So you are now not interested in the second half, but in this part, and so on. Basically, so you basically at each step, you are interested only the half part of that array, and you discard or basically ignore the second half. Okay. So in this way, you kind of, diverge down and you kind of narrow down at each step till the point you don't find that interested element. Okay. So you can find interested element in two ways. Either the first way is you find that element at the midpoint. You are very lucky and you find, for example, you are going to the 500th page and you find the money word there only. So you are very lucky. Okay. This is the first way of finding the interested element. The second way is basically what you will do is you will keep going deeper till the point you are left with two elements only. So now you know that, okay, now which is M? Money. Let us say the first is money and second is monkey. Okay. So now you see that, okay, is this like what is the midpoint? So this is the midpoint. So where I need to go? So I need to go left side, which is money. So in that way, like you drill down to the level where only one element is available, which is your interested element. So that is the second way. Okay. Now, obviously, while deriving the time complexity, we will always consider the worst case. So we will consider the second case where we are dividing the array in half at each step till the point the size of the array is left with the size of 1. Okay, that is the interested element, or if it is not the interested element, you will return -1. Means that element is not available. So what would be the time complexity? So let us say the size of the array is n. In first step, you will reduce it by 2, n by 2. In the second step, n by 4. In the third step, n by 2 to the power 3, n by 2 to the power 4, till the point, let us say, in the s number of step, you have reduced it to 2 to the power s. And let us say at the s number of step, which is the last, the size of the array is left as 1 only. So we are interested in knowing what would be that step where our size of the array will be reduced to 1 if you will keep on halving it. So it will be, let us say, sth number of the step. So we can write it as n by 2 to the power s is equal to 1. Or we can write it as n is equal to 2 to the power s. Or if we'll take both side log, so we will be having log of n is equal to s into log of 2. Or we can simplify it as s is equal to log of n to the base 2. This is the number of steps we need to reduce an array or reduce a number n by halving it each time. Okay, reduce that number to 1. Okay, let us do quickly, because if the length of the video increases, people get disinterested. Okay, so we will just try to wrap it quickly. So this is our number of steps, or we can say that the time complexity of the binary search is big O of log of n to the base 2, because in this number of steps, binary search will eventually either search that number successfully or return -1. Fine. Now, here we have a basic implementation of binary search, pseudocode of binary search. So here we are taking array. This is the first index L, okay, the left index L, the right index R, and the element X, which we have to search. Okay, so if R is greater than equal to L, so this basically determines that your both R and L are positive and L and R are not equal. Okay, so you will always derive midpoint as this one, and then you will check whether your array mid is equal to X. So this is the first case which I talked about. You are very lucky, you find that X into the midpoint. If you find it, you return the index mid and game over. Okay, the second case is let us say if this is not satisfied and it is not returned, so we come to the second case, which is if the array mid is greater than x. So if let us say this is ascending order array, okay, so in that case, if your x is less than array mid, so what you will do is you are basically now interested in the array between index L and mid -1. Okay, and you call again this binary search function recursively. And if let us say array mid is less than x, then you will call this function with parameter as mid +1 as the left and r as the right. So in this case, let us say if this is your array, initially the L is this and R is this. Now the midpoint is this. Now if your X is less than array mid, okay, so if your X, the interested element, is less than array of mid, so what you will do, you are interested in now in this part. So your L will become mid +1 and R will remain R. So you will call the binary search with these two parameters. Same thing. Okay, and you will keep reducing it. Now, a little bit modified of it. In here, we are basically halving the array at each time. Let us say we go to this, again half. Let us say we go to this, again half, and so on. But what about if we will kind of split our array to two parts, three equal parts at each step. So here we are splitting it in two parts, so we are calling it as binary search. If we will split in three parts, we will call it as ternary search. This is a simple pseudocode of ternary search. So we will calculate mid-1 and mid-2 at each step as this formula. You can look at it by pausing this video, okay? And then you compare with whether array mid-1 is equal to x or array mid-2 is equal to x. Then in these two cases, you are very lucky. You just return the index mid-1 or mid-2. If it is not the case, then you compare that whether array mid-1 is greater than x. Appropriately, what you will do is you will take the first 1/3. Otherwise, you will take the second 1/3, or you will take the third 1/3. So in this way you'll do. Now, the interesting part comes. What is going to happen here is we are going to derive the time complexity formula. Okay. So in this case, please notice this is very important part. In this case, let us say if the time taken for n size array is denoted by Tn. Okay. So in this case, what should be the time complexity formula or the recursion formula? You please notice what are all the operations being done here. One operation is basically comparison. Okay, so how many times we are comparing our number? 1 and 2. Okay, and are we doing any other operation? No, right? We are comparing the number 2 times. Okay, and then we are calling the binary search. Based on the comparison, we are calling the binary search 1 time, either this or this. Okay, so what would be the recursion formula? At each step, our time complexity will be reduced to the time complexity of that other or the next half of the array. And at each step, we are doing how many constant operation? 2. Okay, but in this case of ternary search, the same formula would be T of n. Our array is getting reduced to n by 3. Okay, and how many constant operations I am doing here in this case? 1, 2, 3, 4. So I'm doing 4 operations. Fine. Let us work a little more. Now, in this case, if I'll draw the recursion tree, so first time I have Tn, it will be reduced to Tn by 2 plus 2 operation. Next step, it will reduce to Tn divided by 2 to the power 2 plus 2 operation. Again, t to the power, sorry, n divided by 2 to the power 3 plus 2 operation. Can I go a little more down? Let me just make this page a little more taller. Okay, that is fine. But in this case, the recursion tree will look quite similar. Tn by 3 plus 4, Tn by 3 to the power 2 plus 4, Tn by 3 to the power 3 plus 4, till the point we get reduced to the one size array. Similarly here, till the point we get reduced to the power 1. And every time, it will be like plus 2 at each step, plus 2 plus, plus 4 plus 4. Now, if you will see how many total number of operations will be happening here. So basically, this is kind of a, linear tree. What would be the depth of this tree? This will be number of steps in which this n is getting reduced to 1. So we have just seen how many number of steps it will take. Log of n to the base 2. Okay, this will take this many number of steps. Okay, and at each step we are doing 2 operations. In the same way, how many numbers of steps this will take? Okay, it will take log of n to the base 3, and at each step we are doing 4 operations. Okay, so basically the time taken is equal to 2 into log of n to the base 2, and here time taken is 4 into log of n to the base 3. Okay, see, binary search is very, very powerful, or any kind of binary or ternary search. I'll just show you with one example. Okay, you see here, can you know what is the population of world? Current population. Let us say the current population is 7.67 billions. Okay, or 7.9 billions, you can say. And let us say if we arrange kind of genetic information or some unique information about each of the member in this world, each of the human in this world, then and we apply the binary search on that sorted information, then in how many steps we will get the result? So 2 to the power, let us say 33, if I remember correctly, 2 to the power 33 is 8.5 billion, which is almost equal to 7.9 billion, which is the population of the world. So in 33 step, you can find the, basically you can drill down at the array, which is having the size of the human population of this world. So you see in just 33 steps, just 33. So it is very powerful binary search. Now coming back to our, writing board. So this is the time taken here in the ternary search. This is here. Now we want to compare which is more efficient. So let us bring this also to the base 2. So how we can write? For log of 2, we will multiply and divide with log of 2. And this is log of n, log of 3. We will simplify with this term. So we can write 4 into log of 2 and log of 3 and log of n by n base 2. So here, if you will see, we can consider it as 2 log of 2 log of 3 into 2 log of 2n. So this 2 log n is nothing but the time complexity of the binary search. So basically this is an extra term, right, in ternary search. So can we calculate the value of 2 log 3? This one, it will be 2 into log 2. Let us see what is the value of log 2 and log 3. So log 2 is 0.301 and log 3 is 0.477. 0.301 and 0.477. So basically 0.602 and 0.477. So this is obviously greater than 1, right? So it means this term is greater than 1, and hence the time complexity taken in case of ternary search, or I think in case of tertiary or pentary or hexy search or whatever, it will always be greater than binary search, because this constant term will always be greater than 1. So even though by constant term, but still it is greater than 1. So that is why binary search is always better or more efficient than the ternary search. That is what I wanted to derive and present it to you. So thank you for being with me till now. If you like this video, please subscribe to my channel, and I keep presenting similar kind of videos in my channel. And thank you once again. Have a nice day.